Thank you to DeSci Boston for inviting me and for putting this event together. I think it's really cool to just be in a room full of people really optimistic about the future of crypto and its intersection with research, biotech, deep tech. So I think it's just a really cool thing and a really fruitful endeavor. There's two things I really want to talk about today, and mainly from a pretty non-technical standpoint, but of course, I'm happy to dive into the technical details. The two things, the first of one being my kind of personal journey to research, and because of this kind of unique angle I've had, which I'll talk about really soon and on the panel, why I think DeSci is really critical for getting early researchers involved in research. And the second is, specific applications of crypto in biotech. So not just using crypto to improve the means of production for research, but actually improving that last stage of research, so improving products. And I'll give a few examples of that and point out existing efforts that are doing something that I think is really cool. So just get straight into it. I got involved in research at a really young age. I started doing Alzheimer's research when I was 12 years old at the University of Ottawa. So I was working with a professor called Daniel Figges, and literally I would miss high school class to literally play with mice. At the lab at the University of Ottawa. So basically what we were doing is we would give these mice Alzheimer's disease, and we would kind of study the protein changes before and after they had Alzheimer's. And the idea was to kind of understand, how do those proteins change and how does that kind of correlate to humans so that we can understand how these diseases work at a molecular level. So I had the chance to work in this lab for a few years. We identified about 40 novel proteins associated with Alzheimer's, and it was a really good, early experience into research. I knew nothing about molecular biology, knew nothing about neuroscience, knew nothing about research, but was still able to make meaningful contributions to the space. Fast forward a little bit, the pandemic happens, you can't really go to the wet lab anymore, so I had to totally switch it up. And now I started doing AI research. I started working with Richard Nod, who's a professor at the University of Ottawa, and I started working on Neuro-AI, which means how do you use neuroscience to improve AI? So in AI, we have this mathematical tool called, of course, like an artificial neural network. And it's funny, they're called neural networks, but they work nothing like an actual biological neural network. And so what I had the opportunity of doing is working with Richard Nod, we developed a new type of algorithm called PRC models. And we found that these new types of models achieve state-of-the-art performance on spiking data sets. And that paper got published when I was in high school. And again, the main kind of takeaway is that I knew nothing about neuroscience, knew nothing about AI at the time, but was still able to make meaningful contributions. And so when I look back at it, I got really, really lucky. Most high school students don't really have that chance of doing research, let alone publishing, let alone trying totally different things. And when I kind of look back at all these experiences, they've been really critical in my career path. If I never did neuroscience research, if I never did AI, I would definitely not be doing science. I definitely wouldn't be at Caltech, and I definitely wouldn't be studying applied math. And so they've all been really, really pivotal in my career journey. But right now, the way academia is set up, it actually disincentivizes young researchers. So what I mean by that is that if you don't have credentials, it's really hard to get your first research gig. At least for me, when I was a high school student, I knew nothing about any of these topics, and I found it really, really hard to just start off and get the ball rolling. But once you get the ball rolling, you're able to make really cool contributions to the space. So the problems with academia is that, number one, it's not really accessible to young people. You need those credentials. So if you're a high school student, if you're just a university student, it's really hard to kind of get your first gig. The second is that there's a really strong hierarchy that's kind of set up in academia. And what I mean by that is if you're a student, if you're an undergraduate researcher, you don't have a lot of room for creativity or trying new ideas. You're kind of just stuck in this box that the PI kind of carved out for you. And the last one is that it's incorrectly optimized. What I mean by that is when I did research, I found that my professors were spending most of their time doing funding or paperwork as opposed to research. And that's kind of a silly thing. I mean, you spend 20, 30 years of your life trying to be, let's say, the best physicist, the best AI researcher, yet at the end of the day, you're just like writing funding requests to all these organizations rather than actually doing cutting edge tech. So that's why I think DeSci is really important in terms of getting students involved in research. But I want to spend most of my time talking about how we can actually use crypto to enhance biotech and actually enhance a lot of really cool technologies. And so this first space I want to talk about is Neuro-AI, which is what I focused on when I was developing these algorithms with Richard Nod. And Neuro-AI, again, is this idea that we can use neuroscience to improve artificial intelligence, that we can use neuroscience to make AI much more energy efficient. We can use it to kind of create new computations that weren't previously possible. So the first of which is that we know that AI has been just totally blowing up in these past few months, these past few years. And because AI has had such a big impact, if we can even incrementally improve it by like 1 or 2%, it would have a really, really profound effect on society just because AI is just everywhere, it's pervasive. And we think neuroscience is the right tool to hopefully improve AI by 1–2%. And so some of the problems that we see both in Neuro-AI and AI is what I call like the data problem. So if we take a step back, the kind of success of AI has been for 3 reasons. The first of which is the actual mathematical tools have been developed correctly. So we have artificial neural networks, we know how to optimize these networks, et cetera. The second is that we have access to big amounts of data. Without data, we wouldn't be able to train the models correctly. And the last one is that we have the right computing hardware. So because we have the right infrastructure to actually train these models, then we can actually implement these types of computations. Of course, the intersection of big data, the hardware, plus the mathematical tools is what has made AI so successful. But what we find is that, just like what Dr. Roskar was talking today, all these data it's really siloed, and it's really hard to kind of build one model that trains on all these different kind of individual data sources correctly. And so all these data sets are private, and what we actually find in AI is that everyone is working in isolation. And it makes it really, really hard to build proper tools and even compare models to each other. If I build, let's say, the next ChatGPT, and I try to compare it to another supposed ChatGPT, it's really hard to make those comparisons because we're training on totally different data sets. So even though my model might have a better accuracy, how can I really compare that when we're kind of looking at 2 totally different data distributions? And one really interesting application I've dealt with in the lab is with brain-machine interfaces. So when I was in high school, I was really interested by this idea that we can use kind of like computer chips, put them on our brain, and hopefully record neural signals. And one thing I noticed, and this is what Neuralink is doing, by the way, but one thing I noticed is that when I was kind of working on these brain chips in the lab, is that we would have to train them on individual patients. And because of the way that data sources are kind of set up, the way that medtech is sort of set up, you can't train it on multiple people at the same time and kind of pool the data together, because you have like patient identity issues, you have issues with like the FDA and like so many different sources. And on top of that, if you just train it on one person, the data is super noisy. It's really hard to build a really accurate ML model for one person's neural data. I mean, neural data is already hard enough. It's just one person. It's like impossible. But imagine if we could train a brain-machine interface on multiple people, in a group of people. We could pool all that neural data into a server, and we could just train it on the server while protecting patient privacy. And this is something that's totally doable with crypto. It's doable with things like zero knowledge. It's doable with like MPC and multi-party computation. The toolkits are there, but it's just yet to be applied. So this is one really interesting application where I think if we had the right kind of infrastructure to kind of take all these individual data sources and pool them together, we could have a really, really cool impact on biotech, because we would be able to create devices that kind of generalize to large populations, as opposed to what Neuralink is doing right now, where they're only training on individual patients. And of course, your neural data is probably going to be different than mine vs 20 other people. So it'd be a really cool application of, I think, crypto to improve biotech. The second thing I want to talk about is the training problem. So ideally, in AI, you want the algorithm to be kind of the same as the computer. What I mean by that is you want the amount of energy it uses to take the algorithm to actually be like operable. So what that means is you don't want too small of a computer for too big of an algorithm. That's like the ChatGPT case. And you don't want too big of a computer for a tiny algorithm, because that's just inefficient. So you want the sizes to kind of match. But right now, what's happened is the algorithm has just gotten huge. We're in a place right now where the bigger the model, the better it gets. And there's some really interesting mathematical theory of why that's true that I'm happy to talk about. But this is just really unsustainable. And it's really hard to kind of build these models if they're just getting totally out of proportion with the computing power we have. And if we just look at it, if we just kind of plot the number of parameters in the model and compare them over the years, it's literally just growing by like billions and billions and billions of parameters. And there's no reason to suspect this won't continue to be the case 5 to 10 years from now. And in the case of ChatGPT, it literally takes enough power to operate ChatGPT as it is to literally power a mid-sized city. And that's just to actually train the model. On top of that, there's inference costs. So every time you actually operate ChatGPT, you have to, it uses even more energy to run the model on your input. And so one really interesting application of crypto, again, is building these decentralized compute networks. And we talked about it a little bit today earlier, but I think the power with decentralized computing networks is that each individual person can kind of contribute their own kind of hardware. And if each individual person can contribute their hardware, we can make the barrier of entry much, much lower. So what that means is, in the lab, I would oftentimes have to train these really big kind of neuroscience models. If we had some decentralized kind of landscape set up where I could just, rent a stranger's computer and we could pool all those decentralized sources together, that'd be so much easier as opposed to having to go to AWS or having to go to Google and trying to rent out their servers that are already being used to run like ChatGPT. So there's actually an access issue that's kind of at play where I can't even get access to AWS or Google or whatever just because they don't want to set those resources aside to academia. But if we had like strangers just donating their kind of computational resources, we exchange them with tokens or some type of monetary benefit, then we could actually lower that barrier of entry and make it so that anyone can run these types of models just on their handheld devices, which I think would be really cool. And so some good examples of that's already happening is Jensen. They just pivoted out of Entrepreneur First. They raised, I believe, a Series A pretty recently, and they're kind of building decentralized compute networks that allow kind of strangers to donate their own hardware and donate their own kind of computation to run these big models. And the other thing I think is really important is actually kind of integrating DAOs into this. So there's some interesting technologies that are not being focused on right now just because of the funding landscape. So one really interesting technology I've had to work on is neuromorphics. What that means is using neuroscience to improve computer chips. And one thing I've noticed is that because of LLMs, because of ChatGPT, all these big tech companies are putting all of their money aside for LLMs, ChatGPT, just because they're profitable in the short term. But they're not really setting aside that money for really long-term technology like neuromorphics. Neuromorphics are really incredible because they allow you to train models at a much lower energy cost. But nobody's investing in these technologies just because it's not what's making profit right now. It's what will make profit in the future. So I think having DAOs where people could actually vote on what type of technologies they want to invest in would be really key. And it would allow people to really explore really new things that otherwise we aren't exploring because we're literally just in a tunnel doing whatever everyone else is doing. So those are just some really high-level ideas. I'm happy to kind of dive into the technical details of it. I've been working on this for a very long time, so it'd be cool to kind of share ideas and everything. Thank you.